What's wrong? What happened?
I just haven't gotten ready for class.
Oh, it's okay. It's happening very slowly. Very slowly.
Sorry, I'm so tired. I mean, what's new? But I'm so tired.
Shit, I don't have my I don't have my far glasses. I don't have anything. Oh well, fuck it.
It's a Monday.
It's a Monday. 2 more before this week break is in 2 weeks. Oh, it's so sweet.
Fantastic news. I feel like fall semester is always so much harder because in spring there's like 95 breaks.
But there's not. But then after spring break, there's like Easter Friday or Good Friday, like.
Yeah, we're like the only people.
We just get random Catholic holidays off.
Right. He has risen, so
I wish we got
we're
Ash
off.
Wednesday off. That'd be pretty cool.
We get a delayed start on that day, though.
We do what?
Pretty sure.
Do we because of mass or something?
Yeah.
I just always go to mass at night.
Is that like a Thursday or something?
Ash Wednesday?
Yeah. Restart the day. Perfect response. You think Ash Wednesday's on a Thursday, do you? Aw, that's sweet. Good for you, hon. Oh, Lord.
It can be on Thursday for you.
Yeah, we can do a special.
Okay. I remember, like, my first year here, I was married. My first marriage was in a Catholic church, and I didn't know what was going on, and I'm certainly not Catholic by a billion miles. So,
Yeah.
But I was doing it for the woman I was marrying, and I just wait, where am I going with this? Oh yeah, so like I had very little. Like I went to those classes. You have to go to these classes to get married and stuff, and it was all really weird. I'm pretty sure they didn't want to give me a passing grade, but. So anyway, so I didn't know much about Catholicism. So when I first got here, I was like walking around, and there was this one Wednesday, and Tom Leininger in religion. Do you know him, Professor Leininger?
Mm-hmm.
Yeah, tall guy. Yeah.
Oh, maybe once. Okay.
Yeah. He's a nice guy.
We just call him Dr. L.
So much easier.
Now I know it. Okay, yes, I know.
So he's walking down the hall, and I was like, "You've got something on your, you've got something on your head. I think it's dry erase marker." It was like, that was my first introduction to that whole scene.
You know what? And the thing is that you're being so kind that you're genuinely trying to help another person.
I was just trying to help him out.
My favorite, one time it was my freshman year, I went to mass and then I went to the mall with a couple of friends, and everyone at Park Meadows was like, it was like I had a third eye. And I was like, hey guys, I'm fine, nothing's wrong, it's just what it is. I think that's so funny.
I think it's good. Like, have you seen Hedwig and the Angry Inch?
No.
Trinity, have you seen this movie?
I should have by now. But
Oh, come on.
I know.
Oh,
I know.
I've seen it live. I saw it live
I know.
even.
It's called what now?
Hedwig and the Angry Inch. It's like one of my favorite, it's one of the greatest musicals ever created.
Oh.
It's fantastic.
I can agree with
But
that.
there's one of the characters in there, Tommy Gnosis, has this this thing painted on his forehead, and it looks pretty cool.
It looks pretty.
It's like a silvery thing. Anyway, you've got to add that to your list. That has to happen sooner rather than later.
If it makes you feel better, when my parents got married, they also got married in the Catholic Church. My dad definitely was not Catholic at the time. And so, in case you're wondering, when you get married in the Catholic Church, and you're not Catholic, but your wife is, you only have to raise half of your children Catholic.
Done.
You can pick and choose.
I
Isn't
did
that
that.
weird?
That is weird.
Like,
Yeah, that doesn't sound
can
fishy.
you imagine, child 1, you have to be Catholic, but child 2, you can do whatever you want, man.
Oh my god. Oh my god.
Like, that doesn't really make sense. But I love that fact. I'm like, oh, what
That's
a
pretty
special
awesome.
fact.
Yeah.
What a special fact.
Half a zero is 0. I succeeded.
Like, what can I say? Batting 1,000 over here.
Oh man, that marriage was a shit show. But I'll tell you some other time about that. Yeah, I was too young to get married.
Yeah.
Yeah, 22. That's too young to get married. Anyway, do you have any questions on the homework? Have you started the homework? You do have questions.
Yes and yes, but it's not a question that you think.
Interesting.
Wait, you have a what now?
The question about the problem that doesn't exist.
Oh, so I think that maybe I wrote something down wrong. Maybe we wrote something down wrong, or
What did you, let's see, what did I say?
5313 does not exist.
Oh, I don't even have, okay, so here's what I have written down on my list. So
Okay.
5110, did I list that one?
Huh?
523
through 5210. Choose any.
Oh shit, okay,
That was the
wait, that's
first
not,
one.
okay, I got this.
That's
That's an
the
old
one.
version of what I was
Like,
thinking.
Yeah.
Maybe. Oh, I think I just kind of made it up. I was like, I looked at what I had here and then changed it. So I didn't put 510 on there, 5110?
No.
Okay. But I put 525 through 5210, pick any three or something like that, or?
yeah, 523 through 5210.
Okay,
So you choose
cool.
any three, yeah.
531,
Yes.
that's on there. I think that's one we
That-
might need to talk about.
No,
But
that
that
one's
one's
like
too bad.
naming. That one's like, name when R is positive and J is negative.
oh, okay, that wasn't the one because there was.
Everything in 3 is like the fun ones. Those are the Romeo and Juliet stuff.
What did I? Okay, that's good. Is there one with the damped oscillator? Because that
Yes.
should be in there. Which one is that?
That is
13.
Right. That's
Which
5
is
to
in it?
13.
We have that.
5213 is in there.
And right next to 5 to 13, you wrote 5 3 13. But there are only 6 problems in section 5.3.
And you listed 5-3-13 for the rest of the 5-3 problems.
This is also true.
So we're not quite sure what 5-3-13 is supposed
Me either.
Okay, it's okay.
Yeah, I like that cat. You know that cat who
Yeah.
like rocks out. That's me.
I like the cat that does this.
I don't know if I know that.
Oh, I know that one. It's not. Is it really a?
I don't know.
Is it really a cat?
No.
Because it's not. It doesn't look like.
Okay, and then I said 532.
5 3. No,
Five.
5 3 1 4 5 and 6.
Sure, that
Okay.
all sounds great.
Okay, so just get rid of the.
Yeah, I better write this down so when
Yes,
Sydney
is that a cat?
is watching this.
It's not really a cat.
Oh, that one. That's a monkey, right?
I don't know.
It's a monkey cat.
It's kind of a loser.
I better write down this assignment.
I was gonna say, do you want a pen that's not? I have one here.
No, thank you. I do have theoretically.
Sharing is caring if you need one.
Ooh,
Have
candy
it.
cane. I won't eat that now, but
Oh.
that's good.
I thought you said your pen was a candy cane.
All right.
Awesome.
Can you tell me what problems I assigned, please?
Okay.
Like from this top.
5 2 3
Okay.
through 5 2 10.
And
Choose
pick.
any 3.
Okay.
And then 5 2 13. I'm assuming that we're saying goodbye to 5 3 13.
That would seem to be
Yes,
that would seem
okay.
fair. Yes.
5 3 1, 5 3 4, 5 3 5, and 5 3 6.
This is some classic me. I have this list here. It's not at all like the list I ended up giving. So.
And then for the last 3 you go, or for the last 4 you say just fun.
Wait. For the last 4?
Yeah.
No. I want you to do all
No,
of those.
like we're actually gonna do them, but I didn't write that down.
No, you said while at the board you said these are fun. So we're
Oh.
gonna do them because they're just so fun.
Oh, okay.
Yeah.
Okay. I didn't say
It
do
wasn't-
just one. I
Oh,
thought that's
no.
what you said.
Oh,
Okay.
Do
no,
all of
no,
them.
no.
Can I make this any more confusing for you? I'm sorry.
It's all right. Obviously, I'm challenged,
Not-
so
Not at all.
I think you're making fun of me.
I'm making fun of you?
No.
Oh, okay. I was thinking
It'd be
you
pretty easy
not.
to
I don't want to make fun of you.
No, I know. No, it's because I'm sad. You don't make fun of sad people. You're a nice person. I'm just kidding. This is all. I'm just rolling. You're like you're worried. You're not. You shouldn't be worried. You've never said anything close to offending me
Okay, that's
or
fine.
making me feel bad.
That's all I want to know.
That's the truth.
What was the last part?
That's the truth.
Oh, okay, good.
We're good. We're like so good.
Relax.
Unbreakable.
That looks bad.
Yeah,
Let's talk about some problems. This is like,
So-
isn't this what Cyber does? Like you don't
I
do
don't
anything?
think-
I heard some.
We would consistently start class like
Wow.
Like, it's a 50-minute class.
Oh shit. Oh wow.
there were some particular friends in that class.
It's
that-
Hugo.
Okay,
It's
well,
Hugo.
yeah.
Well, we've had this discussion before.
Okay.
Yeah. Who's an awesome guy, but he likes to talk. Just in case. All right, so.
So-
what shall we start with? I don't have my book either.
I have lots of questions.
Good. Fantastic.
I have 0, because I looked at the first problems and I went, I can do this, and then ran out of time.
Okay.
And
Cool.
then looked at the rest.
Well, that sounds splendid.
Okay.
Yes, ma'am.
I do not have the same confidence that Trinity has.
Oh, it's not confidence, it's just being stupid and not having time management skills.
That is not it. Okay, so
Yes, let's roll.
my first question is some of. Let me try again. Okay, so for example, I chose 523 as the first one because I was
So
like, you know
true.
what? Oh,
That's the
great,
one that I was
great. I got really creative and I chose the first
Neat.
one.
Me too.
Cool.
So, I think that there are technically 2 eigenvectors, but when I put them in
May I
the
take a look?
doodad,
The doodad. Oh.
well, no, technically there's infinite amount of solutions because there's 2 infinite solutions, if that makes sense. Do you know what I'm saying? She disagrees. She goes,
No, I didn't finish the problem because
Let me
I ran out
get
of
caught
time.
up with you.
Okay.
And then you can do sanity check, right? So A is gonna be 0, 1, -2, -3.
And then, oh,
Yep.
sorry.
Oh, no, it's okay. Minus, so plus 3 lambda and, is it plus 2?
Yes.
So that's cake,
I know,
right?
that's gorgeous-tastic.
It is. Excuse me. So yeah, there should be 2 separate eigenvectors. So let's take a look at that. Because when the eigenvalues are distinct, you definitely get distinct vectors.
Okay.
So we got lambda equals -2, -1. Which one did you get?
Well, I got, okay, when lambda is -1, I got that V2 is equal to negative V1.
Okay. So you subtracted. I'm doing -1 first, I guess, actually. So you didn't do -1, or you did?
Yes.
What
I got your.
You got that matrix? Okay.
Yeah.
Oh, fuck.
What's up?
Nothing. It's fine.
Can you see that V1 has to equal -V2?
It's just because I'm stupid.
Yes.
No, you're not. So shut up.
Okay.
Okay. So then, okay.
So it's the diagonal down to the right. Yeah, like so.
Yes.
So that is lambda equals -1. So we have an inflow. We have an inflow of both of them because they're both negative. Yeah, does that sound
Have
right?
an inflow on both of them because both of them are negative.
Yeah, so a negative
Both of the
eigenvalue is
eigenvalues
stable.
are negative.
Yes,
Okay,
that's what it is.
okay.
Yeah.
And then, great. So
Alright.
then, okay, I'm feeling way better because I did this last night and I was like, dang, I think I'm losing my marbles.
I don't think so.
So then,
So we get 2v1 equals -v2, so I'm gonna let v1 equal 1, v2 is -2. Or, yeah, they do it like that, sure, better, more clear. Does that make sense? Is that what you got?
why is it 1, 2 and not 2, 1?
So I'm gonna so do you agree, first off, do you agree with that?
Yes, I agree with you.
Okay, so I just replaced V1, I said let V1 be 1, what would that make V2? And then V2 would have to be -2.
Okay,
Yeah,
great.
and so
So then,
they're really close, like this one's like that. And it's still stable, so that's the lambda equals -2. Does that all sound right? Yeah?
Yes.
And then you approach, so you become parallel to the fast direction. This is the fast direction. This is the slow direction.
Because it has a steeper slope.
Yes, and think of magnet. Yeah, that's a good, actually slope's a good way to, no. Take that back. It has nothing to do with the slope.
Okay.
It has to do with the eigenvalue magnitude.
Oh.
So since lambda, we'll call that lambda 2, since lambda 2 is greater than lambda 1, this is the fast direction, and this is the slow.
Okay.
In magnitude, I mean. So the fast direction is the one that things are parallel to when you're way out, far away from the origin. The slow one is the one you become tangential to. So these are gonna kind of look like this. And then over here. Not
Yeah.
all like that. Does that make sense?
Yeah. So it kind of a little bit looks like on the
Shitty.
outside, it'll start to look like a coil.
Yes.
Okay.
I
So it
think.
did drag
So, like,
correctly.
Does this sound good?
Yes.
Like that, that's where, so you're getting to a, like, kind of a spin. This is not quite a degenerate node, but it's on the road to degeneracy.
How sad.
I think that's the lifestyle it's happy with.
So then, okay. I thought you were saying sad face, but not sad face.
No, not sad face, no.
Okay, just
Nothing
kidding,
wrong
just
with that.
kidding, guys. Okay, so that feels way better.
Okay.
All of it makes sense until we get to composing the phase portrait, and then I just get a little lost. But this makes more sense.
Oh, okay, so now that's cleared up though. And then, right?
So those they can travel in between the eigenvectors.
Oh, yeah, absolutely.
Okay. Eat a burrito. So then we would say that 0 is stable. Or
Yes.
do
Yeah,
we
You can say that.
make that stable?
Nothing wrong with that.
Okay.
What else?
Can we talk about the oscillator problem?
Oh, I'd love to. Absolutely.
If you need a textbook,
I
have mine.
absolutely do.
Okay.
Let's see, so we're done with this, right? I can erase?
Yes.
So we got generic mass spring. E is the coefficient of friction, damping constant. Rewrite as a two-dimensional linear system, then classify. Okay. So how did this go for this part? Is this where you're stuck maybe? Yes. Okay, cool.
Because
Yeah.
I look back at our example that we did without a damping constant. And I don't know why, but adding a term is turning me upside down. And I'm not sure how to compose that A vector. Because I know that we need to
Absolutely.
use X and V so that we can get to X dot dot.
Gonna do the same thing here.
Okay.
Definitely. So the first thing, anytime you're trying to convert a higher order single differential equation into a system, you're going to start at the lowest level. So I'm gonna let X dot be called V. So it's kind of weird. Normally we'd say let V equal X dot, so it's written backwards, so it's a little tricky. But we're just noting that the velocity is the change of position, rate of change in position. So that's our first equation. And so then that means that V dot is now X double dot.
Yeah.
And I'm gonna solve for that using this equation up here. So I'll take a few steps on it. K should also be positive, because that's the spring constant. And then M will be positive because that's mass. They're all freaking positive. And so then I would do this. And you see how this is gonna roll now? So this is V dot. This is V. And I've got that second equation now for the system. So V dot is gonna equal negative V over M V minus KX.
Okay. Okay.
Yeah. Trying to do that. Did I do something wrong?
Doesn't K need to be let out of?
Yes, thank you. Yep, solid, absolutely. Thank you. Yes.
Well, that was so much not complicated compared to what I was trying to do.
It's
I
not
don't
too
know
bad.
why.
It's not too bad. So then, like, without getting too much into the thick of it, let's just let's say that our x's and v's are go up there. So we're trying to compose A, and so A is going to be 0, 1, and then negative K over M, negative B over M. And from here, so like I wouldn't like get too much further with this, but I would look at the trace and the tau, and then look at our classification diagram and see what's up. And you should be able to clearly get this into, let's see, I think this is our, this is tau, this is our delta axis, this is tau. And you should be able to get this into a stable spiral or a degenerate spiral. Because, so like, why would that be? Because this is a dampened mass spring system. So if I look at just what X does over time, let's say I've got some initial displacement, maybe even some initial velocity, and that's why it's got a positive slope there, because I kind of gave it a little oomph. But this thing is going to die out. The other option is you have an overdamped system, so you get something like it just kind of goes like that. It might even oscillate once. I think this is called overdamped, and then this is, or one of these two is critically damped, one of these two is, so I think those are the only three possible behaviors, but they don't tell you what's going on in the phase plane. So what you should expect is you're losing energy, right? So I'm losing energy because of the damping. And so this first one here, if I have V and X, think about how this is gonna work. Here my position is at a max and velocity is decreasing, right? Because I'm losing velocity as I lose energy pulling up this way. Not losing energy, but yes, maybe. Does that sound right? I don't know. I don't know if that's the right words, but the velocity is going to be your tangent slope. That's a good way to think of it, right? So velocity 0 when extension is maxed, but that extension gets smaller and smaller, and so does the velocity, even though it keeps hitting 0. So you should see things like, it should look something like that, like a stable spiral, as you lose energy as time goes on.
And we know that it's stable because the motion is towards 0.
Yeah,
Okay.
yeah. And then these two down here would probably look, I mean, this one is just kind of like, one's probably like a semi-stable, like a borderline case. You don't really spiral too much, but you spiral a little. So it's kind of like what we were just looking at with those degenerate nodes like that. And then maybe even, just there's no spiraling at all for that for this one here, maybe. I'm not sure, let's fucking look at it. Let's just look at it. You still gotta write it up and think about it all. And so, because I kind of want to know. So here tau is negative B over M. That immediately puts me in Stableville, right? Because I know that both B and M are positive numbers, so tau is negative. Does that make sense?
Okay.
So if I'm on my tau delta plane, we live down here instantly. In fact, we don't touch this axis at all, so we can't have a center. So remember, this is centers. And then this is just stable stuff down here. Except these are, out here, this is saddles out here. So saddles in this little region. Whenever delta is negative, you have a saddle. Whenever you're down here, you've got stable behavior. And it depends on where you fall with relation to that parabola, whether you're spiraling. This whole region is just stable. That's all I'm trying to say, I guess, down here. So then let's take a look at delta. Delta is going to be just K over M. So delta is positive, which means I'm just over here. Now, what we've done, we've now proved we have to be in this fourth quadrant. So these two pieces of information mean we're in the fourth quadrant of that classification. Does that make sense? Yes. And then let's see, so then the most critical part is what's gonna happen. We really have to analyze tau squared minus 4 delta and figure out, that's gonna tell us if we're inside, because this parabola is exactly tau squared minus 4 delta. So we can, depending on the sign of that thing, SIGN, I'm here, here, or here. And I've got a feeling it's the 3 different cases that I was just mentioning.
Okay.
So let's just take a look and see what that would mean. Tau squared minus 4 delta is going to equal b squared over m squared minus 4k over m. So yeah, I think it depends on the spring constant versus the friction versus all of that stuff. So let's actually get a little bit more here. This is b squared minus 4km over m squared. So the sign of that thing's totally governed by that. So the sign of tau squared minus 4 delta equals the sign of b squared minus 4km. And really what I would just do then is break this down into the 3 cases. So you've got b squared minus 4km is positive. You've got b squared minus 4km equals 0. And then b squared minus 4km is less than 0. When it's equal to 0, this quantity is equal to 0 and you're on the parabola. So this right here is the b squared equals 4km on there. And then I'll just let you kind of do the rest, like figure out which of these regions is the less than, which of these is the greater than. And see if you can maybe just like think about what that means. Like for instance, this one here. In some ways, this says that the damping is stronger than the spring combined with the mass. Yeah, that seems like that would, although I expect spiraling in there, so that just seems like this is called underdamped. So maybe what I'm saying here is garbage in terms of that, like physical analysis anyway. Oh, no, I think I'm right. But I think that when this happens, we're down in here. I think we're in that region. That's why I was getting crazy with that. You'll have to just test that to see. So I think this is like overdamped. This is critically damped, and this is underdamped right here. Because when b squared is less than 4km, your friction force just isn't very powerful relative to the spring and the mass that you attach. So it can't stop these oscillations completely, it can only diminish them. So here, friction, not as powerful. Boy, that's not a physics word, is it? That's friction, not as powerful as the spring. Something like, I don't know, come up with some better language than that. Does this make sense?
Yeah. This makes a lot more sense.
This was the one I was gonna make like a little video and talk about, and then just became incredibly overwhelmed with other shit, so.
I actually like this better because then I can ask questions.
Yeah.
So,
Yes.
why is it, this is probably not a smart question, but why do we only live in the fourth quadrant?
Because when I get this matrix and I crank out tau, that was negative and delta had to be positive because these are constants that are positive.
So it's because it's a physical situation.
Yes,
Okay.
it is because all these constants, because it's physical situation, B, M, and K are all positive,
Okay.
and then that creates this, and that puts me down in here in the
So
stable.
if they didn't have to be positive, we could have a center.
Yes.
Okay.
Yeah, and what would give us a center would be is if there was no damping. So notice that if B equals 0, what do we get? Tau squared, well wait, yeah, if B equals 0, tau is 0, so you're on this line right here,
Okay.
and you're on the center line.
Okay.
And delta would still be positive, so you definitely would have a center, and that's when you have an undamped spring system, and you never lose energy. So you spin
Forever and ever.
forever and ever.
And that's a circle.
That's a circle.
Okay.
Yes.
Alright.
It's kind of cool.
So much physical.
Yes.
So much physical, so much wow. And I think that the Romeo and Juliet stuff makes sense. Some of them, so because they're parameter based, some of it is like evaluate when it's positive, evaluate when it's negative. But so like when A and B are equal to each other, the behavior's kind of boring. But then when one of them is like when they're not equal, then the behavior changes a lot. So then for our homework, how would you like us to show that?
Okay, cool. Let's actually take a look at which problem are we talking about actually?
This is, let me go back. Okay, 4 and I think 5 does it too. Did I not do 5? What the heck? No, it's right here, okay. Yeah, 5 and, no, 6 is really obvious. There's no, robots don't find love.
Oh.
I know, it's very sad. But, here, I'll pull it up on the graph that you gave us. Do you know what I'm talking about?
Yeah, I do. So with the robots, one of just dies, everything just dies out for someone, for the human, because the robot's not responding. Is that what's up?
Yeah.
I was just looking at that flow you
Because
made.
R equals 0, so nothing changes, and so essentially, yeah, it's really interesting. I think it's kind of neat.
This is 536, by the way, Trinity, that we're looking at.
Sorry, I'm not trying to be. Oh wait, no, this is X. Yep.
Oh yeah.
Doesn't really matter what you do. It's
half
changing.
stable.
Yeah, but so when it's equal to 1, they'll never intersect. Or it's this guy right here. This little-
Oh, there
so
is,
did
I
that
see.
wrong.
Oh,
I
yeah.
think I was maybe cross-eyed when I did this.
So there is
So-
some hope in a way, because like, so this line, let me write this up so we can look at it together. Okay, so what was the original?
R dot equals 0,
Okay,
J dot equals AR plus BJ.
okay,
That sounds really wrong.
cool. So, yeah, so you did, so lots of zeros here. So your tau is just B, and your delta was 0. So that means, so since delta's 0, we're on this axis. So I'm doing it kind of a different, like, I don't know if you used this diagram when you were thinking about it.
I didn't, but I think that would make it a lot.
It really
more
helps.
sense.
It's really a great tool. And you're gonna wanna do it when we go to the nonlinear systems, which we might start today. This makes life a lot easier and quicker. So tau is B. So if B is positive, so here's tau equals B, delta equals 0, and this is when B is positive, I'm up here, and then this is tau equals B, delta equals 0, when B is negative, and then here's the super, like, just like everyone's a corpse. Essentially, this is like B equals 0. Notice that it doesn't matter what A is. That's interesting. Oh, that makes sense. I guess, right? So there's no, A, the factor A doesn't matter on any of this. That's interesting.
When you do it on here, it does.
Oh, it'll change the vectors, but it won't change the eigenvalues. Yeah. So the overall, the quality, this is all like quality stuff, right? Not the precision that you're doing. You're doing it in a great, like, precise way, which I like. This is just to gain a general sense of the quality. So this is unstable. And then these are like degenerate nodes here, I think. What do they call them? In the book, what's that little chart? Oh, do you have the book? Anybody have or like PDF or anything? What's she looking at? Oh yeah, let's just look at his diagram though. His like the little quad. That's it. Yeah, that's stars and degenerate nodes. So stars are just like this. Either, there's a stable star, everything's straight, coming in straight. And the degenerate node is when you have a slight bit of spin on it, but not much. So these are degenerate nodes that would kind of be like that. Yeah, and then this node is just everything's dead. Everything's a fixed point, I think, here. So you just start somewhere and you stay there forever. But I would use this to like argue with this problem, because you can it's cool, like it excites me to think about getting the eigenvectors, but like we're just interested in the quality of the relationship, right? So you could just argue, like what we did here, but if B is positive, then we have an unstable position, and I guess you could put that in relationship terms, right? So in B, if B is positive, we have this or this.
Okay.
In
So what do we say when B is 0? Do we say that's a saddle?
When B equals, so we can't hit a saddle, because to hit a saddle we need a negative determinant.
Okay.
And we'll never have that. We'll be right on the brink of saddlehood. We're right on this. We're on this line right here.
So that case is just.
Now you got me wondering. Now I'm starting to think maybe I do want an eigenvector, because like, how do I know? Like for this one, you would. It looks like you would end up in hate or love, but it could be one of these two as well. Maybe these all. Okay, I'm just gonna do it real quick. So let's see. So we've got lambda squared minus tau lambda plus 0. So that, so look, so we do get a 0 eigenvalue no matter what.
And eigenvalue equals B.
And then, yes, because tau is B. Yep, absolutely. So then lambda equals B. So if J if Jay's the kind of person who, they're like, if they're in love, they just get deeper and deeper in love.
Or if they're in hate.
And if they're in hate, they just get deeper and deeper in hate. It's like a positive feedback loop.
Yeah.
But if B is negative, then we'd have something like this, and this means the more in love they are, the they're becoming less in love. Or the more in hate they are, then they're moving in the opposite direction toward neutrality. So this one right here, this would be like if B is negative, and that would be a stable situation where they're kind of, everything's always fizzling out for them. So this is like a fizzle out. This is like, I need some lithium or something like that. Some kind of anti-anxiety, not just some kind of stabilizing pharmaceutical.
Some barbiturates, no, I'm just kidding.
What's that? Wait, what?
I said some barbiturates, those aren't stabilizing.
Those are knocked out. Yeah, yeah.
I mean, assuming that you can find some.
Yes, yeah, yeah. Wait, are you selling these? Is that what's going on?
No, they just get
No, I'm just kidding.
like get stronger over the course of time, which is
Oh.
kind of the opposite of how it's supposed to happen.
Really? That's interesting.
Usually, like your medicine loses strength, but barbiturates increase.
Like, so like, how does their potency go? Because they have like a half-life, right?
Right. So it interacts with the air, and so it actually increases potency.
For how long? Like, and then eventually it starts to die off, right? So there's.
Probably not. There's a reason why some medication must be in a very specific bottle. Like, doesn't touch light, doesn't touch.
You're talking about it becomes more potent as it sits on the shelf.
Yeah.
Or whatever. I thought you were like saying as it in the
Oh, in your
bloodstream.
body.
I was
No,
like,
no,
that
I'm
sounds
sorry.
terrifying.
So like
Got it.
if you found some barbiturates from the 1950s.
That's crazy because of the oxidation. Wow.
Yeah.
Interesting.
That's also why we don't give them to people anymore because.
Yeah, they'll keep them and they'll become deadly.
Well, or it could do something unexpected in your body because everybody has a different method of, or not method, but a different rate of oxidative phosphorylation.
Interesting.
And one more question about
Yeah,
this example.
let's do it.
So if you're like in the negative J example,
Yes.
so if everything's always fizzling out, does that mean that like sometimes it just like jumps? So like things can be going really, really great and then, oh man, I'm done. You know what I'm saying? Or are we not considering that kind
Well,
of?
you could. So you could have a behavior like this. So because of this kind of these twisty things, you could have, let's say you had an eigen direction like this, and then it was, so that's a possibility,
Okay.
something like that. So you're not, things are pretty crazy and intense down here. You're like literally having a horrible relationship with a robot.
Yeah.
You might want to like consider the way you
Being
approach
done.
life. You're like fighting with Siri. This is like my mom, like fighting with Siri down here. And then realizing that Siri is a robot and there's nothing to fight about.
Okay, good, makes sense.
Does that help
Yes.
a little bit? Yeah.
I don't know why, but I a little bit struggle to go from math to relationship.
Yeah, I think it's a pretty weird leap.
I mean, how else are you gonna? I like it. I'm not saying I don't like it. I'm just.
Oh, I didn't think you were. It's weird, but it's fun.
Like it.
So I would say take this problem, take this information and then present it, whatever analysis you want to use. If it's like the charts you made, you always do a great job. I'm not worried.
Okay.
Not the least bit worried.
I didn't want to like attach it. Like, look at this link. No, I'm just kidding. Of
Are we
me
good?
pushing through it.
Yeah. Are we good?
Oh yes. I'm sorry.
And we're good, because you didn't have any questions to begin with. But maybe now all the questions you could have had would be answered. Sure, we'll go with that, right? Yeah, okay, good. So could I start on something a little bit
Yes.
new?
Yes.
Fantastic. It's
I
not really that
apologize.
new. It's not. I mean, questions on homework. That's what I had listed as our top priority. So
I
we're
just feel
all
like I have
good.
95 questions.
You have what?
I said I feel like I always have 95 questions.
They're always great. I'm always like happy you have questions. Like I plan on people having questions. When people don't have questions, nobody's doing anything. So this is great. So we are going to take, this is our toolbox. So the linearization, not the linearization, we're about to talk about that, but the eigenvalue analysis using that little chart like we did, that's gonna be one of our key, just go-to skills. And if we need more detail, then we'll get eigenvectors. But in general, really we're just gonna worry about eigenvalues. When we analyze a nonlinear system, nonlinear 2x2 systems of differential equations. So here we're gonna have x dot equals f of xy and y dot equals g of xy. So a lot like what we've had, except that this isn't an ax plus by cx plus dy form. So these are not going to be linear equations. And so here's how we'll proceed, our plan. One is we're going to find all fixed points, all equilibrium solutions, i.e. where both fxy equals 0 and g of xy equals 0. So we want to find a spot where everything's just stopped. These are simultaneously that. So let x star, y star be such a point. We'll do it, and then we'll do an example together. Then step 2 is we're going to linearize about each fixed point. And this is our microscope. Let's talk about how that's going to go, because we need to do a Taylor series expansion, but it's in 2D, so you probably haven't seen a lot of those going on. It's not the kind of thing you use very regularly. We're going to do the series expansion of this system. And the way this is going to work is as follows. First off, I'm going to do a change of variables. I'm going to let u equal, make it x minus x star. So this is going to be, now again, I'm assuming that x star, y star is a fixed point. And what I'm going to do is move a little bit away from that to a point xy. And I'm going to let uv be the displacement. So v is going to be the vertical displacement, u is going to be the horizontal displacement. And that's what I'm just writing when I say this. The perturbation away from make sure I'm on the right track again. This all looks good. So what we're going to do is change variables of the whole system. Now, you're not going to do this every time. So we're going to devise a mechanism using this analysis, but you're not going to go through a change of variables every freaking time. So if this is my change of variables for u and v, what does u dot become? And what is v dot? Look any further than the last 4 lines. this is U. This is V. What is U dot V dot? Yeah, right, because that's a constant. Yep, beautiful. Got that. So that's going to make this become U dot, and this is going to become V dot. So that's done. And then what we're going to do is use this also. F of x, y can be written as a Taylor series in 2D around the point x star, y star. And the way this is going to work is as follows. First off, it's just f evaluated at the center of the series. So x star, y star is our center of the series. And then I've got the first derivative of f with respect to x at that point. Now, normally what I would put here is x minus x star, but we're just going to put u here. So if you were doing normal Taylor series, you would put x minus x star there. And then plus f at y of x star. So this is partial with respect to y. X star, y star, v instead of y minus y star. And then out here, I'm going to have higher order terms. So they're going to be u squared, v squared, and u times v stuff. And these would be like the second partials, where those would come in. So second partial with respect to x, second partial with respect to y, and then mixed partials for x and y, respectively. We're going to get you your uv term. And then we're going to do the same thing. Ooh, I haven't done this in a while. Oh, I just figured something else out. Oh my God. No, that's okay. That kind of, but this is pretty sweet. This feels really good. G of x, y is pretty much the same thing. So just underneath, just except instead of f, I've got g. And then higher order terms out here. Does that big O notation make sense when I mean there? Yeah. Let you get caught up. Oh, we'll get to that in a minute. Does this sounded reasonable? Cool. Anything I can simplify here? Anything? It's not explicitly written on the board, but it's like something we're assuming about x star and y star and their relationship to f and g.
F of x star, y star is 0.
Yeah. And same for this one, right? They're both dead there. And then we're going to ignore these higher orders. So we're assuming that u and v are very small magnitude. So in that case, in certain cases, most cases, we can ignore the big O terms. And I'm going to talk about when it wouldn't be okay after we actually get this analysis done. So we're going to assume that x star, y star is such that we can drop the higher order terms when magnitude of u and magnitude of v are very small. And this notation's pretty standard, I think, right? The double, that's like super small. Have you seen that, Trinity?
Mm-hmm.
Yeah, okay. And I'll put a little note, I'm just saying a note to you, note to the whoever the hell's watching this stuff that's not in this class. We're gonna talk about why, when that's not gonna be okay.
I'm sure Sydney will watch.
What's this?
She won't be here.
Who's it?
Sydney. I'm sure that she
Oh,
will watch
Sydney's
today.
totally gonna watch this, I believe that.
So we'll have an explanation for one.
We'll have one of the views will make sense. So, we're gonna drop those, these are 0, look at what we get. This gives us an approximation, a linear system. So remember now this is now u dot, because it was x dot. This is v dot, because it was y dot. And those two are equal. So my new system is u dot equals partial of f with respect to x at the fixed point, fy at the fixed point, that's a v, and then v dot equals fy, x star y star v, oh excuse me, this is g, whoops, g with respect to v at the fixed point v, and I'm just gonna go straight to a matrix form. uv dot equals this matrix here, and we'll just put a little star because it gets kind of old writing the of x star y star. It even gets old just saying it. So these things here represent those functions, those derivatives evaluated in x star y star. Oh, how about a UV here? Okay. So, said it like 5 times, I'm still gonna write it for the sake of notes. All right, that's it. So that's like the price we paid. Basically what we did is we've got this fixed point, we linearized around it, which means blow it up, and this is the microscopic version of the behavior, bless you. So this is the behavior local to that point. So this models local behavior near fixed point. And we're gonna go and classify it. So we're gonna do this for each fixed point in the nonlinear system. We're going to, so what did I call this, step 2? Something? So then step 3 is classify using evals, evex, the diagram, whatever you want. Sometimes we'll get more precision in there if we want a better, sometimes things will not be clear, so we'll maybe pop out a few eigenvectors to understand flow in or out and know exactly where that direction is. Overall, it's not gonna be the thing that's most important. The diagram and the tau squared minus 4 delta is gonna be where a lot of things go. And so then classify and then put the diagram together. We're gonna have things that are flowing out. We're gonna have sources, we're gonna have sinks, we're gonna have spirals, we're gonna have saddles, and we've gotta like put the flow together in the plane in a consistent way. Put the diagram together in a consistent phase portrait. So let's do one together. This is uncoupled. There's no intertwining. I have to run to the restroom. Could you figure out where the fixed points are? I'll be right back. There are 3 of them.
That is so loud. I'm so sorry.
You're
Good lord.
We got them?
I think so.
Where be the fixed points?
0.
0. I need 2 coordinates, so.
0, 0.
0, 0. Where else?
When x is plus or minus 1.
There we go. Cool. Set that equal to 0. Solve. The other one's easy. And when this one's equal to 0, the only way that happens is when y is 0. So that makes it sweet. So then this is this. And from that we get our 3 fixed points. Yay! Nicely done. Step 2, linearize. So this matrix here, and I forgot to say it, this is called the Jacobian.
I
Is it?
feared.
Does that sound right? Yeah, you've done this. What?
We glossed over it. It was like, this is the Jacobian, and then we walked away.
Where?
Numerical. Have you seen it elsewhere?
Yeah.
Okay, sorry. I'm sorry.
Yeah.
No,
I don't remember exactly where, but yes, I know it.
Anytime you're doing calculus with like a change of variables, Jacobian
Yep.
is going to be.
Yep.
Calc 3, you must have seen it. They may not have called it that.
I took
I had
Calc 3 in
Calc 3
high school,
too.
so I don't think we have.
You
words
took
like
Calc
that.
3 with me?
Yeah. First semester of college.
Oops.
Okay.
I don't know if we talked about it or not. Maybe.
That was a rough semester.
It was, yeah, that was.
I think
We
it
didn't
was
have
in-
computers.
It's true.
I think it was in my E&M class or something. It was in some physics class.
It makes sense. That makes sense. Did we talk about it in complex because it relates to the
We
Cauchy-Riemann equation?
We could have as well.
Yeah, maybe. Anyway, it's all that's good. It doesn't, knowing that or not knowing that isn't gonna stop or
You're
make
still gonna
anything
use it.
happen. What's that?
We're gonna use it.
You go, okay, yes.
Yeah.
So we'll call it J. So we're gonna find J of X, Y, and this is probably something you would just wanna crank out at the beginning of this whole process because you're gonna plug every single fixed point into it. So the Jacobian is gonna be partial of this with respect to X, partial of this with respect to y, partial of this with respect to x, partial of this with respect to y. That's the general Jacobian, and then we're going to evaluate it at our fixed points. So, J at 0, 0. And oh, I got some cool tricks to show you too. Make our life better and better. We got 0, or put in 0 here. We got 1, 0, 0, minus 1. So now I don't even have to go to the characteristic polynomial, the lambda squared minus tau thing. I can read, I know what the eigenvector values are. Do we know what the eigenvalues are? What do you think they are? They're 1 and minus 1. I know that because if I have a triangular matrix, in other words, a matrix where a diagonal half of it is 0. So you got a matrix like this. It doesn't matter what size. You got stuff along the diagonal, and you've got 0 in one quadrant or the other. The eigenvalues fall on the diagonal. Always. So when you have a triangular matrix, you can read them off. So look, I have a positive eigenvalue and a negative eigenvalue. What kind of behavior is that? I've got an outflow and an inflow. What do you call that? Outflow one, inflow the other? Yeah.
You're like, that's not a
That's not quite what I'm going for. Saddle.
Oh.
That's what I'm thinking, because I got opposite flows. If if they were both like working together, then we worry about slow fast. Does that sound good?
Yes.
Yeah. So this is going to be a saddle. So we have a saddle at the origin. Cool. And we can find the vectors for that if we want, but we're going to see if we can get by without it. At 1, 0, we've got -2, 0, 0, -1. Did I do that right? Yeah, I think so. Now slow fast shit for sure. I got a stable node because I have 2 negative eigenvalues, right? Does that make sense? So this is going to be a stable node, with 2 negative and distinct eigenvalues. So I'll have 2 distinct eigenvectors as well. And then look, J at -1, 0 is the same thing. So stable for both these. These both have the exact same nature. Does that make sense? Is that right? Yeah, I guess that has to be right. So let's get the phase plane out.
So does that mean that those are distinct fixed points then? If they give, like, I know that they're separate, but if they give the same behavior, then
yeah, they are distinct still, because one's so like one's. Well, first off, here's our buddy saddle. Here's stable node here. Here's stable node here. So that's 1. That's -1. So I know this saddle has. Shit, I think I will get the eigenvectors for that saddle just really quick, because I kind of want to see where the influx and outflux is going. So for 0, 0, we have lambda equals +1. So my matrix is going to look like 0, 0, 0, -2, 0, V1, V2. So this is actually going to be super helpful. Super, super duper helpful. So for the outflow, that happens when, notice this says V2 is 0 and V1 is free. So this is, in other words, the x-axis. That was super good information. So here I've got outflow on the x-axis. That totally syncs with these having to be stable. See how it's coming together. Let me stop because I'm getting excited, moving a little fast.
Can you say V1 free?
Yes, so notice here that the top equation would be
Yeah.
0 equals 0, and then down here, v1 times 0. So the only thing that is forced, sorry, I should look this up. The only thing that's forced out of this equation, the eigenvector equation, is that v2 has to be 0.
Okay,
Does that make sense?
perfect.
Yeah, and everything else can,
V1 doesn't matter.
v1 doesn't matter, it can be whatever it wants. So that means I've got a vector that has no vertical component. And look, that totally makes sense. So the outflux of this saddle at the origin is straight across, right into those sinks. These are sinks. This is acting like a source in that direction. And then you could easily convince yourself that the other eigenvector is the inflow, is going to be on the vertical axis. Pretty similar analysis. And then 1 and -1 are just stable nodes. Look at how beautifully consistent that is. That means, think about how saddle trajectories go. Once you've got the heart of the saddle, you just add consistent lines with that flow, or lines that are consistent with that flow. And they have to end up in these sinks. And then the rest of this, this is pretty sloppy, but there's a lot of this kind of stuff going on. It doesn't matter. I know that, and actually I could get a little more subtle, right? Because there is a slow direction and now there definitely is a slow direction and a fast direction. Looks like the way this would have to be, think about how the saddle's approaching tangentially. It seems like the slow direction would have to be this incoming one, just to make this portrait be sensible. Things are going to be smooth and consistent. So with very little effort, we just analyzed a fairly complicated system and now completely understand its qualities. We'll do way more of this on Wednesday. This is so much fun. This is one of my favorite things to do. I think like I say almost everything is my favorite thing to do, don't I? I say it a lot. I'm just a very enthused human being.
I'm pretty sure that there are much, much worse things.
That's true. That is true.